Hello, very good morning to all of you students. How are you? I hope you all are happy, healthy and fine at home. What did we learn yesterday? Yesterday we discussed about the steric control and how with the help of example we have learned how the steric control or the stereochemical control can be done with the help of the example we have. What we are going to learn today, let us see here, we already discussing about the second point according to our syllabus, the concept of chiral templates, chirons, wherein the carbon skeleton is the chiral precursor. That is the main point we are discussing here. What is chiral template, what are the chirons, what type of the carbon skeleton or the framework present in that, and the chiral precursor, and ultimate aim to synthesize the target molecule by considering this chiron approach. That is what type of the precursor or the template we are using, that is a carbohydrate. Another one is mainly as a carbohydrate is the main precursor we are using to synthesize the natural product in the organic chemistry. That is the ultimate aim. So today we are going to discuss about steric control, conformational bias and anomeric stereo selection. What does it actually means, how it is applied? Here is a one example, scheme number 7, which is given, is a very beautifully is explain what does it mean, what is the steric control and the conformational bias, how that anomeric stereo select and how it is used, that is here explained. Let us see here is a target molecule. As we know that target molecule means the molecule whose synthesis being planned is known as a target molecule, and this is one of the target molecule which is medicinally useful, and that's why it is considered here. And this the example, the name of this big molecule, complex molecule is a erythronolide A. So this is one of the natural product, and how the scientists, the segments are given here, 1 and 2 segments are there. One is a what is that, carbohydrate segment, and as we know that carbohydrate type symmetry, it may be apparent or hidden or partially hidden. That type of the approach we are generally finding here while synthesizing such a target molecule. And now look at here the one of the skeleton or the segment which is apparently seen in this target molecule. If you look at the carbon framework or the carbon skeleton in this particular molecule erythronolide A, so here you will see this one is a carboxylic acid, alpha or hydroxy carboxylic acid, as well as this is a carbohydrate skeleton, and mainly four precursor we are generally using here while studying as a chiron approach. Number 1 is a carbohydrate, second one is a hydroxy acid, third one is a amino acid, and fourth one is a terpene. By using these precursor, we are trying to find out, trying to synthesize the molecule in the laboratory, in the research lab. Look at here. Look at, this is a disconnection arrow, and as we know that disconnection means what? It is an analytical operation of breaking down the target molecule into convenient starting material by using FGI, and the FGI is known as a disconnection. This is a disconnection. While disconnecting this bond, you should keep in a mind, you have a method, you know the method to form the new bond, carbon carbon bond, or you can synthesize this, and this is a chiron. And as we know that chiron is a combination of chiral and the synthon, these two words combined together, and only this type of the two chirons we are getting here, chiron number A and chiron number B. What are the differences here? Only at a carbon number 5 and carbon number 5 there is a R group at 6th position. Here at 6th position is a hydroxy group type of the substituent present over there. It is just like as in the carbohydrate type of symmetry, apparent symmetry you can clearly see here. This is a chiron 1, this is a chiron B. Two chirons are there. By combining these two chiron, we will get only one apparent type of the precursor we are trying to find out here. Here if you put as a double bond here, or we can extend or we can reduce the bond by using appropriate reagent, and we arrive at that chiron, so that we will get as a such type of, here we are bringing as a carbon carbon double bond methyl group over there, and this from chiron we can get as a this template, and as we know that chiral template means what, or the chiral template, chiral molecule means which the carbon atom carries a 4 different group which exhibit or which shows or which establish the optical activity. And as we know that optical activity means what, the certain substances rotate the plane of polarization through certain certain rotation, or what we can call it as a certain angle is known as a optical rotation, or that is a optical activity. And the instrument used to determine the optical activity is a polarimeter. Polarimeter is used as a instrument to determine the optical activity of the organic compound. Here is the chiral centers are there, 1, 2, so these are the chiral center, and as we know that in the previous, while making their chirality sense, the precursor or what we can call it template should have a chiral, and then we, because the main purpose we are approaching the perspective of that must be the chiron over here, carbon carbon double bond. And now we can prepare this, could be made from this, the arrow indicate this could be made from this could be made from this. And now here disconnection, so here is a carbonyl group is here, so we can insert methyl group over there, or the hydroxide just by reduction, or you can carry out the reaction like as some organometallic compound you can use over there. You can insert as a what we can call as Gilman reagent, or the what we can call it as a Grignard's reagent, so that you can insert the methyl group across that carbonyl group, and just by reducing this we will get as a hydroxy group over there. And therefore this is a one way to get this one, or this compound can be obtained from this. Look at what are the changes is done here. Here this OR is above 1, just inverted. By inverting it, by rotating that single bond, we can change its configuration, means invert. Invert means just opposite to that one. And anomeric carbon, look at the anomeric carbon, we are not changing as a anomeric carbon. This is a anomeric carbon over there, and that is a methoxy group is present over there at this is an anomeric carbon, anomeric center, this one we are keeping as it is throughout in this. And now this one again inverted, so Mu over there. Now this can be prepared from this one. Look at this group, this hydroxy group we can oxidize, we will get as this type of the carbonyl group over there, OR, Me, OMe and RO. it remains as it is. Now this compound can be prepared from this one. Look at here, here is a RO dash, oxidize this one, carbon this one, and here is we are protecting that oxidizable group over there, and you can reduce this. After reducing this carbonyl group, we can convert this very easily into as a hydroxy group like this OH and OR dash. Rest of the thing remains as it is, and this compound can be easily obtained from this one. And look at here is a epoxide. Epoxide can be obtained by just treating as a peracid or the H2O2 hydrogen peroxide across that carbon-carbon double bond. If you have a there, then and then this ring, epoxide ring, that is a 3-membered heterocyclic ether rings are there. It can be easily opened, and we will get as a this type of the precursor is obtained of this target molecule. So this is about the steric control, conformational bias, and the anomeric stereo selection. Let us see the more general explanation regarding this one in a related approach, but using an additional conformational bias and anomeric stereo selection, one can construct a cyclic segment. These are the acyclic segment, and these chiron are the cyclic segment. Macrolide antibiotics as well as other natural products that are derived from the propionate or polyketide biosynthetic route. The hidden carbohydrate type symmetry in erythrolyte A, for example, can be related to 2,6 carbon segment. That is a scheme number 7. This is a scheme number 7 is shown here nicely, corresponding to the chiron A and B. Right. In such a cyclic segment, we find 2 hydroxyl group which correspond to C3 and C5. Correspond to C3 and C5. Of hexose, chiron A has 2 C-methyl groups at C2 and C4. At C2 and C4, the chiron A has a 2 methyl group, C-methyl group. There are the 2 methyl groups that belong to the L series. L specifically series is considered over here. Chiron B has 1 C-methyl group at C2, a branch point at C4 and a branch point at C4 here. Look at here is a tertiary hydroxyl groups present over there, branch point at C4 and a D configuration. And in 2 chirons share to the some substitution pattern and sense of chirality if C2 and C3, and they each harbor to the C5 oxygen atom in the ring protected until needed. In addition, beta contains a C-methyl group and a tertiary hydroxy group at C4. Hence, it can be used in a B as an intermediate to produce A, provided that the configuration at C5 is inverted and the hydroxyl group at C4 is removed. And the sequence shown in the scheme 7 illustrates how this analysis can be capitalized upon, starting with the methyl alpha D glucopyranoside. One begins a systematic introduction of functional group based on the aspect of conformational bias and anomeric stereo selection provided by the axial orientation by the anomeric structure, anomeric substituent. The 4 keto derivatives serve as a povital intermediate for both chiron A and B, and which in turn are converted to a cyclic equivalent chain extended and eventually linked to the provide the carbon skeleton of the target. So this is all about the this one steric control and the conformational bias anomeric selection. In the next lecture we will see about the transfer of chirality, how the chirality get transferred with the help of example that we will see in the next lecture. I think let us stop today here. Thank you. Have a nice day.